In this lecture, we will discuss different types of bonding and how the types of bonds affect the material's properties. Hopefully, the previous lecture with periodic trends did prepare you well enough to consume this material. Okay, so let's start with the primary bonds, right? The There are three primary bonds, and what we need to know about those, since we call them primary, what we mean by that is that they possess large interatomic forces. To break down a primary bond, you do need to deliver a sufficient amount of energy. Now, there are three primary bonds, and those are ionic bonds, covalent bonds, and metallics. Okay, now before we jump and discuss each individual bond, we need to understand why elements tend to bond, right? Why atoms tend, once you bring them close enough together, they tend to bond instead of coexisting on their own. Well, or in other words, what is the driving force behind the formation of bonds? And you will probably see me asking you this question in exams or tests because this is really, really important. Why elements tend to bond? Well, because when bonded, the potential energy of each bonding atom is lowered. And when the potential energy is lowered, that means that the element or the material exists in a more stable state. I'll give you a very simple example, but I really want you to understand this point, right? We each have 2 feet, right? And we preferentially always stand on 2 feet, right? You do have an option of standing on 1 foot, but you wouldn't do that, right? And I mean by completely removing the second foot off the floor, right? You could do that, but you won't do that. Why? Because standing on 2 feet lowers your potential energy and allows you to reach a more stable state. Okay. Now, if I offer you a chair, you'll probably say thank you and you'll take the chair because sitting on a chair lowers the potential energy even further. Okay. This is a very basic example, but I really want you to understand why I'm bringing it up. So for the atoms, once you bring them together, there is a reason they tend to bond because once the bonds are formed, the energy is released. And the reason the energy is released is because the potential energy of each element that is bonded is now lower. And the lower the potential energy, the more stable state the element exists at, right? Same with you, right? Standing on 1 foot is pretty unstable. Sitting comfortably on a chair is a very stable state, right? Hopefully that makes sense. Now let's jump into the discussion of each of the bonds. It's going to be relatively simple and relatively straightforward. At least I'll do my best to keep it simple, okay? Let's start with the ionic bonding, okay? So, the ionic bonding exists between elements with large differences in electronegativity. And if you do not recall what electronegativity is, I'll bring back this page right in here. And I will remind you, electronegativity, it is the degree to which atom attracts electron to itself. So that means that for the ionic bond to occur, you want to bond two elements in which one is very generous and is willing to donate or give away electrons, and another one is very, very greedy. So it's kind of like a tug of war, right? But one of those doesn't even resist because the more electronegative element always wins and it always pulls the electron its way, right? So, but whenever you have those two elements that have large differences in electronegativity, the degree of the element, I forgot the definition. I have like, how do I say, the degree to which the atom attracts the electron to itself, right? When you have elements with significant difference in electronegativity, that's when you have the ionic bonds. And what that means, right? Well, that means that the electrons are transferred from electropositive to electronegative atom. The electronegative is the one that has the largest electronegativity or the greedy atom. Now, once this happens, once the transfer occurs, right? So once again, I'll demonstrate here. You have electropositive element, that's the one, the generous one, right? And you have electronegative, the greedy one. And that facilitates, once you bring them close enough, that facilitates the electron transfer. Once that occurs, you now actually, you don't have neutrally charged elements anymore, right? You're looking at a positively charged cation and a negatively charged anion, right? And whenever we have those, that means that there is going to be an electrostatic force of attraction between cation and anion, right? And there's going to be always this force that keeps them together, and that force is going to be your ionic bond. Very strong forces, and it takes a significant amount of energy to rupture, to break down that force, right, and separate the cation from anion. Okay, just a little bit more on the ionic bonding. I give you a very rough preview of what happens there, but I want you to kind of like understand, right? Okay, so you have a plus and a minus, and it's not that you bring them close together and they just click together, right? It's not like a magnet with a south pole and a negative pole. It's a bit more complicated. And since we are familiar with the structure of an atom, I want you to understand a bit more what actually happens as you start bringing electropositive atom and electronegative atom closer together, right? As you close the distance between those two. Well, let's just go over a few steps. Positive nucleus of one ion will attract the electron cloud of the other ion and vice versa. And it makes sense, right? Well, I have a positively charged nucleus of my one element, it doesn't matter which one it is, and it will be pulling in the electron cloud of the other element. But the electron clouds, right? The electron clouds of both ions, they will repel each other when they are sufficiently close, right? And that's why it's not like sticking actually, because now that you have this clouds coming closer and closer together, right? The closer they are together, the larger the repulsive force will be, right? Now, meaning that there are two forces that come into play, right? And there's the attraction force and there is a repulsion force, and they are actually drawn right here. I will show you this way, right? And this is your force F, right? So there are two forces coming into play. Now, at some point, these two forces, attraction and repulsion, will balance each other, and there's a specific distance. And that happens at the equilibrium interionic distance A sub naught, and that's when the bond is formed. Okay? So if I am to introduce the concept of a net force and allow me to maybe perhaps do it like this, I now want to introduce the concept of this net force, okay? And the net force, it's as simple as the sum of attraction and repulsion, right? Now, at some point, the net force is zero. And I want you guys to understand what is the net force. Let's say I'm holding someone's hands and we hold each other very tight and we rotate each other, right? We kind of like we are in this motion. And the net force between the two of us is actually going to be zero, right? And I don't know if I gave you the best example, but what I mean by that is that no, it's probably a good example. I'll try to explain it again. The centrifugal force, because we're trying to rotate, right? And together, the centrifugal force pushes each of us outward, right? And that's going to be a repulsion. But we are holding on to each other with all the power we have. That is the attraction, right? Because you're kind of like fighting for your life there. So, and you guys can imagine that perfect moment when the attraction is in perfect equilibrium with the repulsion. And that means that the net force is attraction force is there, the repulsion force is there, but the net force is zero. And this is exactly what I'm describing here, right? So for the net force to be zero, we will have to be somewhere in here, right? This is your zero. okay, right? When it intersects, and the distance at which it intersects our axis X is going to be your A naught, and that is going to be this distance right here. Okay, this is the interionic distance. And that means that this is where the bond is formed. Okay, so hopefully it makes sense. The net force is zero. Okay. Okay, now, since you're looking at a graph, right, this is not a sketch, and I'm referring to the graph on the left, you see that there is a traction force, you see that there is a repulsion force, there is the net force, which is just the summation of both, right? This is not a sketch. There is a mathematical equation that allows you to calculate those, and you guys see this equation right here, which is for the net force. One thing to keep in mind is that this component here is going to be your attraction, and here is repulsion. So you can actually estimate both, and this is how you can plot them the way it is plotted in the bottom left corner. Now, the formula is very, very easy. This Z1 and Z2, this is just the number of electrons removed or added during the ion formation, right? You keep in mind is that one element gives away, another element accepts, right? So this is just the number of the electrons. E is as simple as the electron charge, and this is a constant. This eta sub naught is going to be your permittivity of free space, and you can see this number right here with the units, and N, and oops, no, not N. Oh yeah, N and B are constants, and the A is the distance, right? And of course, you can change the distance on this specific graph, right? It's going to be this distance right here. And A is something that you can actually change, or you can estimate. Obviously, if you ought to put the interionic distance in there, then the F net should equal 0, right? Now, perhaps we're going to look at the example. We're not going to solve it because it's just basically units and plugging in the numbers. But let's look at the sodium chloride. Okay. We have sodium plus and we have chlorine minus, right? And when the bond is formed, there is basically it's one electron, one gives away the electron, the other one accepts the electron, and that's why for sodium we will have +1, for chlorine we will have -1, right? Chlorine is, it would not be good of me not to bring up the bar to show you perhaps even this, right? Doesn't have a chlorine in here, so I have to stop in here. Let me find the sodium and chlorine. So with your permission, let me delete this, right? I know that chlorine is highly electronegative, so I'm going to use the blue color. Here's your chlorine, right? And it's highly, highly electronegative. There are only a few elements that have the higher electronegativity than chlorine. And here's your sodium, right? And that's a perfect example. These two are separated by a significant, significant difference, right? And that's how you know that your sodium is going to end up as a cation because it's going to donate the electron, and chlorine is highly electronegative, right? Very electronegative element. It's going to pull the electron its way. And as I was saying this, chlorine is here. I can actually put it here, and then this is your sodium. So in a sense, you could use that bar too. Usually within this course, I'll never tell you what the bond is, but I'll ask you what type of bond is formed between this element and this element. And that's how you can look at the bar and think, well, this is a very significant electronegativity difference. And that means that one of the elements will steal away the element because it has a higher tendency to accept, right? Now, going back to the question. So one electron, right? This is the electron charge. This is permittivity of free space with units. Yep, all correct. I was checking the units. The A naught is the sum of radius for sodium. And keep in mind is that the sum of positively charged and negatively charged ions. You may be wondering, where did the numbers come from? Well, the numbers come from the textbook, from the appendix in your textbook. Keep in mind that there is one table where you can find the atomic radius for the element. Make sure when you solve a problem, and if in the problem you are actually dealing with a positively charged or negatively charged ion, then you need to refer to the table that actually uses ions instead of elements. It's a different table, okay? Yeah, and then you plug in the numbers, and this is going to be your force. Since it asks for the force of attraction, this is your force of attraction. We use the first term in the formula, right? Because the second term is going to be your repulsion. Don't worry if I ever give you, some of you may be wondering now, well, what if I'm asked to find the repulsive force where you have this and B constants? Do not worry if I ever give you a question like that. I will always supply you with all missing values, okay? I have to ask it. Okay, so sodium and chlorine, right? Sodium and chlorine. Sodium is tiny here, and chlorine is big, right? And since we just learned the trends in atomic size, I want you to look at here, okay? I'm going to switch the color. I want you to look at the sodium, okay? Sodium right here, and here's your chlorine, okay? So we know that the size increases from right to left, right? And the reason chlorine is so tiny, and I'll remind you, because we are hosting more and more protons, right? And what happens is that the nucleus charge effect is stronger. The electrons are pulled toward the center a lot stronger, and the size shrinks, right? So chlorine is tiny, sodium is large, and it makes sense, right? Because this is the trend in atomic size explained by the nucleus charge effect, right? Now I'm going back to this slide, and you can see that the size is flipped. And this is not a mistake. I'm just trying to emphasize what exactly happens. The reason your sodium now is so much tighter and smaller, and it's actually significantly smaller than negatively charged chlorine, is because this is not a sodium, this is sodium plus, right? Larger charge of the nucleus significantly shrinks the size of sodium. This is just an example. Just in case if somebody noticed it and was wondering. Now, I'll say one more thing is I'll just give you an example of a problem that you could encounter in one of the exams. I can give you this graph, okay? And it does say that this is an ionic bond. And I'm going to ask you to label the interionic distance on the graph. Okay, so how would I do that? Okay, well, first thing is that I know that this is my interionic distance, so it's somewhere in here. And I do need to find that point that tells me that the bond is formed, right? And so the point here, since this is an ionic bond, and I know that the driving force behind the formation of the bond is minimizing the potential energy, and I'm looking at the energy, right? And I know there has to be some kind of minimum, right? So that means there's the minimum, right? Because this is my net energy. This is what I would draw, right? And that means that this distance right here is going to be my A naught. I could ask you something like that, and you're probably wondering, and right here I'm saying that the net energy is minimum when ions are at equilibrium separation distance. Some of you may be wondering, well, how am I supposed to answer that question? That question is no different from the net force, right? The net force right here. Oops, not here. I actually used this slide right in here. One thing to keep in mind is that when the bond is formed, the net force is zero. But at the same time, the energy, the potential energy, right? The net energy is also zero. These graphs are very, very similar. The only difference is it's just whatever you have on the y-axis. But regardless of which graph you will see, well, keep in mind is that that graph is going to be photoshopped a little bit, so a lot of things will be missing, specifically the bottom portion that actually shows you the interionic distance, right? This A naught, that thing will probably be gone. So just by understanding what is bonding, right, lowering the potential energy, and then when the bond is formed, the net force is zero. And what is the net force? You should be able to identify a point like that. It's usually it's not a tricky question, but a lot of students tend to not being able to answer that specific question. All right, now most important and most interesting part. Well, how do I link the bond to the material properties, right? Once again, we're discussing the ionic bond. Now, what we know about the ionic materials, right, or materials with ionic type of bonding, is that strong electrostatic forces hold atoms together, right? We know that there is electrostatic force that is very, very strong that holds these atoms together. Now, the electrons are tightly held inside the bonds. And just giving you a little bit of a preview, or maybe you remember from some of the earlier lectures, is that in metals, electrons are like a pool flowing there, available, shared by everybody. There's a different picture here. Every electron is tightly held inside the bond. Now, what this means is that it brings us a bunch of these properties, and specifically, I'm wondering if you would be able to recognize the materials that have ionic bonds, okay? High melting temperatures, and it makes sense because the bonds are very strong. You need to supply a lot of energy to break down the bond, okay? The materials are hard, meaning that they don't dent. The materials are rigid, they don't bend. They're also strong, that means they don't break. Well, they do not break up to a certain point because every material yields at some point. Now, they're brittle, meaning that they deform little before fracture, and they're excellent insulators. Why? Because all of the electrons are tightly held in the bonds, and you can't conduct the electricity if you don't have available electrons, right? Well, perhaps I should say not just electricity, either electricity or the heat, right? And so hopefully people now recognize, well, that is ceramics, right? Now, I'm going to talk a little bit more about this brittle, right? Everything else kind of makes sense, right? Strong, hard, high melting temperatures, excellent insulators, all this makes sense, except that brittle, right? Why would they be brittle? That means that they don't deform. Why don't they deform? Okay, well, the bonds are very strong, but there's more to it, right? And I'll explain it with this picture. And I want you all to envision, hopefully at some point you did own a ceramic dish or bowl or cup or maybe a vase that you dropped. And hopefully you do know what happens, right? It breaks into pieces. And if you ought to take the pieces, you'll be able to connect them back to each other because they're not deformed at all, assuming that you find every single piece, right? But why it fractures and doesn't deform? Because I want you guys to envision a metallic wire. You can actually roll it, you can wrap it, you can bend it, right? And it's not gonna break. At some point it will. If you do it too often, you'll know why that happens too. But overall, right, if I am to take into consideration this material, why does it fracture the way it does? Well, because if you are to take the external force, right, and if you are to apply the external force on a compound that is ionic in nature, and that means it basically has alternating charges, minus, plus, plus, minus, minus, plus, right, plus, minus. So now I'm going to apply the electric force and the charge is going to shift. And all of a sudden you have this plus, plus, minus, minus, plus, plus, and like all the way to the end. And the like charges, they repel, right? And we know that. And that's how the crystal cracks. Okay? So hopefully now you were able to link the ionic bond to material properties and maybe even to a specific class of properties, such as ceramic. Because that now, going backward to what we learned about ceramic, maybe now it makes sense. Okay, this is why ceramic is chosen as an excellent insulator. It is an excellent insulator, either heat or conductor, because the electrons are tightly held within the bonds. The bonds are exceptionally strong. The material is brittle because of what you see on the slide and things like that. I do want you to start thinking deeper about all of these concepts and kind of like connect all of these concepts together. Now let's go to the covalent bonding. Covalent bonding is one of the easiest, and I'm going to go very fast through these slides. But still at a pace that allows you to consume the information with comfort, right? Covalent bonding exists between elements with small differences in electronegativity and mostly nonmetals. Um, Something to keep in mind, guys. Covalent means almost fair. Okay, so typically that means that the atoms, the way they bond is that they share. It's like a perfect roommate situation. Sometimes there's a little bit of a disparity, and you may look at a polar covalent bond, or in a very perfect world, it's non-polar. And usually it's non-polar when the elements are the same, right? But anyway, so the whole concept is that the atoms bond through sharing electrons. This word is extremely important. That means is that it doesn't belong to either of the element. It actually belongs equally to both. Okay. And I'll give you an example. You have one hydrogen, right? And you have two hydrogens, each has an electron. They come together and they form a bond, and they're going to share these two electrons. And basically, a bond is formed between two atoms by sharing for this specific example, 1s1 electrons. It doesn't have to be a single bond. You can actually have a double bond. For example, when you have the oxygen, right? When you have these two oxygens coming together and they end up sharing four of the electrons, meaning that they will have a double bond. Okay. And then what else? Nitrogen is gonna be sharing six electrons, right? Meaning that you will have a triple bond. Okay. All right, now hopefully that makes sense. There's a little bit more I want you to understand about the bond order and the bond length, okay? So, and specifically the energy. With a higher bond order, the energy will increase. And it should make sense, right? It takes effort to break down one bond, okay? And there's a certain energy. Well, now that if I have to break down triple bond, I'll have to supply a lot more energy, right? So with higher bond order, the energy increases. But when the energy increases, the length shortens. So the length also shortens. And hopefully that makes sense. Okay. And I'll give you an example like this. Okay. I'm looking at the carbon and I'm looking at the carbon-carbon, single bond, double bond, and a triple bond. And if you first let's look at the energy in kilojoule per mole, you guys will see that the energy increases as the order increases, right? Increases. And at the same time, the bond length in the same direction decreases, right? I'm not sure this arrow kind of makes sense, but hopefully you guys remember that I give you kind of like this explanation, okay? I added a note, even though the direction the same way, right? But the trend is different, right? The energy increases and the bond decreases. Okay, let's look. I have an issue with loading my slides. All right, so let's answer the question. Based on what I just told you, I want you to connect the length and the energy, right? The order here wouldn't matter. Which bond has the highest energy? And I'm giving you carbon, right? And you have this carbon on the left is always carbon, and you bond the carbon to iodine, bromine, and chlorine. Okay? And I want you to think for a second, take your time, pause the video before I jump into the explanation. I'm jumping to the explanation. The bond with the highest energy is going to be the shortest bond, okay? Even by the size, I just know that iodine is a lot larger than the chlorine. And the shortest bond, right, as the length decreases, the energy increases. Okay. There's more to that. You could also you could also try to answer this question by thinking about the electronegativity. Again, chlorine is going to be more electronegative because you guys know the trend, right? The trend is kind of like upward, diagonally upward. Chlorine will pull the electron its way, but with that, again, it comes down to shortening the bond. That's probably no better way to say that. Okay. Now, covalent bond, something to keep in mind is, as I said, you may end up with either a nonpolar bond, right? And the definition is pretty straightforward. That means that the sharing of the electrons is equal, right? And usually that happens when you bond same elements, right? Oxygen, hydrogen, nitrogen, fluorine, and things like that, right? The same element, they have the same electronegativity. The electronegative difference is zero, and that's why there is a fair sharing, right? Or perhaps I should say there is a fair deal in terms of sharing those electrons, right? Now, you may end up with a polar covalent bond when that means that the sharing is slightly unequal, right? And I'll give you an example. For example, you may take into consideration the hydrogen. I know that some of you may be thinking hydrogen is really in the wrong place, right? And hopefully you guys will notice it um, not just with this graph, but I'm sure that some of you have been noticing that hydrogen should really be moved, right? Should really be moved like somewhere in here, right? Yet it is not there, okay? Um, okay, so what I bonded to bromine, I lost my thought. To bromine right here, right? So if you look at the difference, there is a difference of about 0.7. So in a sense that you don't actually have a fully ionic bond, but you are looking at the covalent bond. But in that circumstances, there is a polar covalent bond. And it kind of gets tricky. Right now, you're probably thinking, okay, you need to tell us what the cutoff, right? What is the difference? What should be the difference to determine whether the bond is polar covalent or ionic. And perhaps one of the ways to answer that, I will jump to that slide right away because I just realized I think it's a good way to jump to that. Sometimes when we need to understand, well, what kind of bond is it, right? Is it a ionic or is it polar covalent, right? When it's a non-polar covalent, it's very, very clear. And how do I define how much of ionic character the material possesses, right? Well, all you guys do is that usually it's called a mixed bonding, and usually we define it as the percentage of ionic character. And here's the equation, right? And it's 1 minus exponential, and maybe I will rewrite it like this. Maybe it's going to be slightly better. You guys will have negative delta x divided by 4, okay? And all of this times 100%, right? So I want you to understand what this delta x is. The delta x is the difference. X here is electronegativity. It's the difference in the electronegativity. Electronegativity difference, okay? And you guys can imagine just looking at this equation that the larger the electronegativity difference, the higher the percent ionic character. And that should make sense. It's not very important, but I'll try to explain it. You're probably wondering, well, how how can I see it from the equation? Okay, for those who are interested, I'll explain it. If you're not interested, you can just scroll it, okay? Let me put my delta x in here, and let me put my, this is going to be your e to the power of negative delta x. And if I am to draw it, it's going to look something like this, right? Okay, so this is what the graph is going to look like. And right now, guys, I'm looking just at this thing. Okay, so the larger the delta x, the larger as the delta x increases, your function itself, I'm gonna put the difference here so you guys clearly see it because it's a negative. It's important that there is a negative sign. As the delta x increases, your function, you guys can see, it decreases, right? Goes almost to zero. And that means whatever is in the brackets is large because you're going to have 1 minus a very, very tiny number. You're going to like 100%. And hopefully now that makes it makes sense how the entire equation works. The larger the delta x, the larger the ionic percent ionic character, and it should make sense, right? That means that the more the difference in electronegativity, the more ionic character you have in the compound. Okay, hopefully that makes sense. Now going back to metallic bonding, right? We're done with covalent bonds. Keep in mind that covalent bonds are also very, very strong, right? And it's happens through equal sharing or fairly equal sharing. Metallic bonding, right? What we need to know about the metallic bonding is the following. Okay, so metallic bonding is weaker than covalent bonds. Okay, now atoms share a pool of free electrons, and I kind of want to pay your. I'd like you to pay attention to this figure that we see. Usually metallic atoms, they're not really neutral atoms. They're rather positively charged quarks. Why? Because the electrons are like floating everywhere. Okay. So you don't really have like equal number of protons and electrons because these electrons, they're like everywhere. And this is all this gray area is going to be your valence electrons. Okay. So in a sense, every atom shares all of the electrons, and that's the beauty of metals. Because if you need to conduct either, excuse me, if you need to conduct either electricity or the heat, this is only possible. This entire operation is accommodated by the electrons, right? And in metals, you have this army of electrons readily available to conduct either electricity or the heat. Now, pure metals are ductile, meaning that they are very soft and malleable. And now, one thing to keep in mind is the number of valence electron increases, the melting point also increases. And you can look it up here so you can see, let's say if I'm going from potassium to calcium, I am increasing the number of valence electrons. And if you look at it, the melting point, I really don't like how, like really increases, but I have to, yeah, I have to point it downward, but I'm just showing you that it increases in calcium, right? And you can look up other elements um, and just see those trends. Okay, so now what does it mean, metallic bonding and material properties, right? So how do I explain it? Well, uh, pure metals are significantly more malleable than ionic or covalent network materials. And that should make sense, and I'll explain you why, guys. Okay, so if I am to apply the external force, right? you have these positively charged ions, but they're always balanced out with this sea of electron, right? This electron sea. And so what happens is that the metal just deforms. Okay, and here's an example. Like they just smashed it and kind of flattens, but it's still fine, right? It doesn't crack because you don't have a scenario that you have with ionic compounds where you have like charges now aligned with each other and now they have to repel and the material crack. This is why with metal you kind of like have something that is very, very malleable, something that is very, very soft. But I don't want you to get the impression that, oh, it's weak. It is not weak. Of course, it depends on the thickness, right? Because if you take something that is made out of metal and it's kind of like thick and chubby, right? Like bulky, I said chubby, bulky, I don't think you can actually like bend it the way you would bend a wire, right? It's just kind of one of the examples. And again, pure metals are excellent conductors of heat and electricity. Why? Well, because of this electron sea, going back to that, right? Now, few more things I would like to talk about the bonding, right? And up to this point, we discussed primary bonds, right? Ionic, covalent, and metallic. And hopefully now, guys, if I tell you all aluminum, right? Compare aluminum to aluminum oxide, right? So one is metal, another one is ceramic. So just even if I just tell you these two, right, without even defining that one is metal and another one is ceramic, you should be able to do that, right? Because if you take aluminum oxide, you go to the chart with electronegativity and you start thinking, okay, what's going to happen? Is there a difference in electronegativity? Is there going to be a charge transfer? And if that's the case, you can start predicting the properties, right? Well, one aluminum is going to be a beautiful conductor, another one will not, right? Because there's going to be the ionic bond and things like that, right? So that's kind of like the whole point of why we started with structure of an atom, what happens to our electrons, because all of these properties define the bond. The type of the bond defines the property of the material, right? And outside of the primary bonds, we also have to be aware of the secondary bonding, and it is very, very simple, but it also has a very significant effect on the material property. Usually, the secondary bond, they exist or they occur due to attractions of electric dipoles either in atoms or molecules, right? And so what does it mean? Well, what is a dipole? It's demonstrated something right here. For the dipole to occur, you basically need to have a positive and negatively charged center, right? Usually you have a negative pole and a positive pole. And one of the ways to think about it, it's like tiny magnets coexisting. And of course, if you have plus minus, they will be kind of like interacting with each other and they will interact through electrostatic, or we also know those as Coulomb forces, right? Now, one thing to keep in mind is that those dipoles, they can be either permanent or fluctuating, right? There are two different types. And I will give you an example. Let's start with the fluctuating dipole. The dipole can be created due to asymmetrical distribution of the electron charge, right? So what does that mean? Well, the electron cloud, right? The electron cloud in the atom, it changes with time. And at some point, right, in figure A, you guys can see that there is a symmetrical distribution of electron charge. It's kind of like everywhere. And that's why you have this plus and minus and it kind of like balances each other. But in picture B, you have a just at the specific moment, right? Just at this one tiny, tiny moment for a nanosecond, probably even less than that, you have this electrons shifted toward a certain area and that creates this area right here, right? This area right here. Because it is deficient of electrons, it's going to be positively charged. And that's how I end up with a positive and negative pole, right? And all of a sudden, this atom is not a neutrally charged anymore. Just for that 1 second, as it fluctuates, it exists as a dipole. Okay. Now there are also examples of permanent dipoles. And that means that these dipoles, they do not fluctuate with time. They actually exist as is, and they are permanent. And I'll give you an example. Let's consider the CH4, right? This molecule, okay? And that is what it's made of. And you guys can see that you basically have four carbon-hydrogen bonds, and there's just a symmetrical arrangement of those bonds, and it means that there is no dipole moment. Now I'm going to take one hydrogen, doesn't matter which one, but I'm going to actually remove it, and I'm going to replace it with chlorine. So all of a sudden, I'll do that at the bottom. Okay, chlorine. Chlorine is more, you guys know that chlorine is electronegative, right? More electronegative element. It's going to pull an electron its way. And what's going to happen is that in here, you will kind of have a negative charge, and above, you will have like a positively charged. So now you have like, there's asymmetry in the arrangement of bonds, and all of a sudden you have a dipole, okay? And that means that if you're looking at the C of these molecules, that means that there is this additional interaction between those molecules, because you have plus minus, plus minus, plus minus, right? And they're basically fluctuating because they have permanent dipoles, right? Okay, hopefully that makes sense. This brings me to hydrogen bonds, right? Hydrogen bonds is basically an example, a perfect example of a secondary bonding, and we even call this hydrogen bonds, right? So by definition, hydrogen bonds are dipole-dipole interaction between polar bonds containing hydrogen atom, right? And it's usually hydrogen oxygen or hydrogen nitrogen. Now, and I'll give you most known example, which is water, right? And just as an example, if you guys take water and you take hexane, heptane, toluene, benzene, ethanol, acetone, ethyl acetate, all of those liquids are a lot heavier, right? Because they have a bunch of carbons and hydrogens and oxygens, yet they evaporate a lot faster, right? That means that for the material to evaporate, that means that the forces between molecules are very a lot weaker than in water, right? Because to boil water, you need to raise the temperature as high as 100 degrees C or 212 Fahrenheit, right? Why? Because of the hydrogen bonds. The hydrogen bond exists between this hydrogen, this is your hydrogen, guys. This is hydrogen, right? Which is positively, oh, I just saw that I have a mistake. This is your positive, this is your negative, right? Because of this interaction, right, electrostatic interaction, you have this permanent dipoles, right? And they exist everywhere. So if I am to evaporate the water, right, I need to break down that bond. And that's why I have to supply a lot more energy to water than to hexane or other compounds. Some of you may be very familiar with any of those. I'm sure some of you were exposed to either of those liquids, and you probably know if anybody opens acetone, not in a fume hood, but they open in front of you, you can sense it, right? You can sense it everywhere because diffusion takes place really fast. You don't even need to heat it up for the solution to leave the surface, right? Now, I just explained it, right? But I see the mistake. Oxygen is our negative, right? Negative pole, my apologies. And hydrogen is your positive. How do I know that? Well, very simple. If I am to take oxygen and hydrogen, I know that oxygen is more electronegative element. And I'll even bring up this guy right here, right? So my oxygen electronegativity is 3.5, hydrogen is 2.1. So I do know that the oxygen is the one that's going to pull the electron its way and create a negatively charged pole. With this, we conclude our learning module number 2, and I'll see you in the next lecture.